So what I want to do is now to do the derivation of the Yefremov effect starting from this eigenvalue equation for the bound states phi nu, which we left off yesterday. And that is a quite neat, nevertheless, technical and mathematical chain of arguments. But I find this quite appealing through those complex arguments, and also that there is some intuition gained through that. Towards the end, I want to at least mention or summarize the status of the contact pionless EFTs for larger objects, meaning anything going beyond 3 particles, and also touch upon there the higher order corrections and the peculiarities you encounter there compared to other EFTs. But this is only for the end, and for that I will show you something on the projector because that is easier. But now let's start with this eigenvalue equations. So what we established was that any function phi nu which satisfies this equation, namely an eigenvalue equation for this operator k, where we had this rather complicated form written out yesterday, with an eigenvalue 1 corresponds to a bound state of our interacting system. Now, and that means that this energy is negative and is part of the bound state spectrum. Now we can analyze this equation also for energies which do not correspond to a bound state energy. Then in general, this equation will be also an eigenvalue equation, but now for an eigenvalue which becomes also a function of this parameter, the energy, and g, which is the coupling constant. So in all our derivations, this g can be replaced by the two-body scattering length via the two-body amplitude and the renormalization conditions encoded therein. And for our purposes, we are interested in the case where g is slightly below the strength which is necessary to bind a two-body system. So I'm not yet at the point where the two-body correlation length is infinite. And that means it's, we consider cases where this is smaller, where this critical G2 star, which is the point where A becomes infinite. So this is mainly important for convergence purposes and the mathematical structure and characteristics of that kernel. And this is now the function we want to analyze and investigate and see whether or not we can find a point or some trace of this becoming infinite for all. So this is of course also particular for any eigenvector nu. So there are certain features of that kernel which are important from the mathematical perspective. I don't want to bore you too much with that, but this kernel is, just to compact, to summarize the things you have to check before jumping to conclusions about the properties of that. So it's a very humbling exercise to go in detail through that derivation, because if you make a mistake at some point, if you forget to check certain aspects of such a kernel, all your tower of arguments and deductions breaks down. So this makes this a very, to me, advanced and intriguing exercise, which is most likely why it has been forgotten for a long time. So it's a compact operator. It's square integrable. And what else? It can be made through a unitary transformation to be a Hermitian operator. So given all those properties, from that it follows that the trace of that operator here to the power of n is equal to the sum of those eigenvalues also to the power of n. So this is a theorem from, not only linear algebra, from the theory of integral equations, that any function of this matrix here, or matrix in quotation marks, it's an infinite matrix, is equal to the function of the eigenvalues themselves. Okay, so this is then basically the sum of the diagonal, and right. Here an operator? Yes, but the trace is no longer an operator. So once I take the trace, it's no longer an operator. So K is, K was defined. All right, so what also follows from that is, and that is important, is that the eigenvalues here are monotonically increasing with G, so the absolute magnitude of G. So if you make G or the interaction more attractive, the eigenvalues here also rise. And 1 over E. So this function here is an increasing function in G and the inverse of E. And that is important to understand now how we can get from this some information about the bound state characteristics if we start with a certain energy E and a set of, so, and this is what I wanted to sketch because I had really a hard time visualizing and understanding that argument. So first thing to note is that taken as a function of E, once this eigenvalue here becomes 1, it is by definition corresponding to a bound state. So what I'm looking at now is the functional dependence of those eigenvalues on E at a G which is almost identical to that where the scattering length is infinite. So what I plot is, and this is now a bit counterintuitive, the eigenvalue spectrum. Let's do this here. Or not the eigenvalues as a function of the energy. So this is a bit a convoluted way of thinking, but I tune the energy and I look at when do certain eigenvalues here cross 1. And once they do that, they count as a bound state. So, and the interesting thing which we might find is that there's an infinite number of those crossing 1. But this should be a result, not something which we are looking for. So how do we get that out? So first, so G should be a value which is close to that where the two-body scattering length is infinite. So this is important for taking this limit E going to 0. So this is what we eventually want to do. We want to consider this sum here, or I'll write it as the trace, a to the power of n, in the limit of E going to 0 and A going to infinity. And that limit A going to infinity is identical to the limit of G going to this G critical for the two-body interaction. So this plot is a plot where G is frozen, set to a specific value. Okay, so from those properties, I also can deduce that I can order the eigenvalues for a given energy. So for some energy, for which I'm considering that eigensystem, I have eigenvalues ordered in a certain way. I don't know how many I have. So here I have my mu1, mu2, mu3. So this is what I can assume, and it's always that, no, the other way around. I chose that smallest index is the corresponds to the largest eigenvalue. Yes, it's the greater or equal rotated by 90 degrees. Sorry. They shouldn't. No, that is not something which is so the it's not clear that they cross 1 at all. That is not yet. This is the so this is something we don't know. But how do we know that they must cross 1? So this is something which follows from analyzing that trace. And this is a very interesting phenomenon now, which I have not fully understood. So substituting for this k, the integral we wrote down yesterday in coordinate representation, with the G being a renormalization scheme dependent coupling constant, gives us an expression. So this is a calculation which is straightforward, not easy, but can be done. I'll skip that. And it follows that you get a, now I write this as a function of lambda, A plus another constant. So this is the functional form which this trace of the kernel K assumes a constant, then the logarithm of some function of lambda times A plus another constant. And here you'll see now that this trace, namely the and this, so no, this is not true. This happens in the limit E going to 0. So in general, you get a finite expression. If E is not 0, you have an additive term here, a constant in the logarithm. This is something you can, or I shouldn't say that, it's, I'm not sure how you do calculations, but evaluating that trace, for example, that's an integral. And you can spend a long time on doing that with pen and paper, but Mathematica is quite good in doing that for you, or any kind of AI system. So it is not difficult and not tedious. It can be done in a minute. So don't, I always have this hesitation that I feel that I'm stupid if I use the modern calculator, but I think this is not something one should be ashamed of. Okay, and this is where you see very quickly, if you don't set E equal to 0 in that kernel, you get a form which is no longer divergent if A goes to infinity. And that is, but if you set E equal to 0, or let E go to 0, you'll find that this form here is the one which diverges logarithmically with A. Okay, this is what it is, but I can't readily tell anything from that yet in terms of the evolution and the properties in the limit E going to 0 for those eigenvalues. For that, there is something much more intriguing. What is happening, namely, if you analyze the limit E going to 0, not of the trace of the nth power of the kernel. So that is something which is important intuitively, as you're not only considering, so what was this kernel we looked at last time? Now we still have Easter eggs. It was equal to such a diagram here. So an amplitude here, and then a free Green's function before the thing hits the wave function, which I symbolically denote by this square is equal to the wave function, where you should, or where I think of this square as a sum over 3 diagrams with a certain weight. So this is also something very unusual to consider. So how do I diagrammatically depict a bound state or a wave function? But this is you can translate as a sum of 3 momentum states with a certain weight factor, which corresponds to the wave function. And that is the connection which is, which connects quantum mechanics with quantum field theory. So you identify certain sets of such asymptotic states, weight properly, and those weights obey the equations of quantum mechanics. But that's just as an aside. So this is the kernel, and to obtain the solution for that diagrammatically, it's usually necessary to iterate that. So iteration means I take infinite powers of that in the hope that this whole thing converges then. And for that reason, looking at such an object is of interest. And that is also why this the result of that calculation is so very interesting. So for that, I just wanted to show you how you obtain that result given that you know what this result is, because it entails a very neat trick connecting the whole calculation to few body physics, or a certain set of few body coordinates. So what is this trace? Again, please, there are factors missing and I might mess up signs. But the trace of that iterated kernel is equal to, now I write the kernel as a function of P and P prime again. So it still remains an energy of a function of E and G, but I also make explicit the representation in which I consider this kernel. So it's a function of, no, it's a matrix in P1. So the iteration is then P1, P2, and so on up until Pn, and then again P. The reason why I have P here and P here is reflecting the fact that I'm taking the trace or the diagonal, and the integral goes over P and P1 to Pn in three-dimensional momentum space. Okay, so it's worth writing that out, at least roughly. So I have from the measure of that object, which I d e I equal 0 to n. I do that for the S-wave component. I haven't talked much about the angular momentum decomposition. This is important for what comes later in order to find out in which partial waves or in which angular momentum states I find those phenomena and in which I don't. But I do this in an S-wave projection. So the partial wave decomposition of those kernels here. And then I have in the numerator a product of P squared, P1 squared, Pn squared, and dp. Now in the denominator, I have from each kernel a P squared, Pn squared, no, let's call that a Pi squared minus Pi plus 1 squared minus Pi dot Pi plus 1. That as a product of I equal to 1 to n minus 1 times E minus a P squared minus P1 squared minus P1. And then I'm still have to take into account the Easter egg, which is in the limit or in a specific or specific interaction now, 1 over a minus square root of minus e. So this a you can replace with the coupling constant of our low energy effective field theory. This e here is the cut, and this becomes in the limit of a going to infinity, no. This becomes an E. Yeah, right, sorry. So remember that we had here this product of T E minus 3/4 of P squared. So I evaluate that here not at E, but at this energy. I take E to 0, and that leaves me with a square root of P squared. So I get a P here, or I, and here Pi to N. For each of the kernels, for in the limit of A being very large or infinity, this brings me down in the denominator. So this here translates into a product of Pi's times E squared, I equal 1 to N, for each of the Easter eggs. Okay, so now what do I do with that? If I only have one of those kernels, so not those products here, I find that it's logarithmically divergent. So this is what you find immediately without problems, even by hand. This is not so hard to see if E goes to 0. This structure here is more complicated to evaluate or to see immediately what kind of divergence, or if it has a divergence at all anymore. So how do I do that? The first thing, does that depend on N? So naively, one would expect that the divergence gets either worse with the power N or disappears completely. So one of those two things would be the intuitive outcome of that. But this is why this is so surprising. None of that happens. So, and how can I see that? And this is very nicely seen if now I switch to a different set of coordinates. So here I'm using this coordinate set P, which characterizes the distance between the particles. I have an high dimensional integral. And for the analysis of those systems, nuclear and atomic physicists use usually so-called hyperspherical coordinates. If you haven't heard of that term, it's worth thinking about if you want to characterize, or if you're dealing with systems where the size of the object is a characteristic quantity, because those coordinates define for, let's say, a certain U-body system. So I don't give you the equations, but they define just a single dimensionful quantity, the so-called hyperradius, which characterizes the size of the set of particles and a set of angles. It's a generalization of the notion of spherical coordinates, where you define one dimensionful radius and then a set of two angles, which characterize the geometry of the object. And hyperspherical coordinates are the generalizations of that, where you define also for a set of now n points, just one dimensionful quantity, which is the so-called hyperradius, or rho, which is defined as the square root over the squares of the different radii. This is something you can express also in terms of relative coordinates, in terms of Jacobi coordinates, and so on and so on. But this is the only dimensionful quantity in my system. And all the other quantities are angles and have no dimension. And they determine the relative orientations of the different subsystems with respect to each other. So the details are not so important, but or they are important, but I will skip them. If you re-express this integral in hyperspherical coordinates, what comes out is, so you need to express the measure in hyperspherical coordinates, and that gives you a rho to the power of, so I think it's 3n minus 2 d rho. So this is the measure here. Let me see if this is correct. No, it should be 1. 3. No, 3. Yes. So we can check that for one particle. No, minus 2. For one particle, minus 1. I should have r squared. Yeah, so minus 1. Okay, in the numerator, I can evaluate. So what you see, and that is also something to note, is that this divergence, where if there is a divergence, from which end of the area of integration does it come from? It doesn't come from the ultraviolet piece, because that's where the coupling constants in my T renormalize my theory. It always comes from the zero, so from the very low momentum region. And then I need to concentrate on those pieces. So E is going to 0, so I don't have to worry about that. So I have to investigate those parts where all the momenta go to 0 simultaneously. So where there is no where the power of the momenta is identical to the other ones. So the important contributions of that are just those which are the p to the power of 4. Wait. Now I think I'm missing an argument. So this is a product of n of those factors, and the question is which of those p's is most significant in terms of creating a divergence in or a 0 in the denominator. And that is the one which has a product of all of those. So all the ones which with p squared and so on, they combine with others such that the product is always finite and doesn't harm us. So what is then left is a product down here of I equal to 0 up to n of pi times p. And that's it. And now I need to look up what are those PIs, so the individual magnitudes of the momenta in terms of the hyperradius. And that's a complicated, a horrible formula, but it's always proportional to the hyperradius times some function of those hyperangles. So, and this n here is actually small n. So what this gives me then is, and now I hope I did not make that mistake. No, I think it's the product of the squares. Yes, not that one. That should be. So if I substitute that in, what I find is that my integral over the hyperradius from 0 to infinity is 1 over rho. And with that, so here, that calculation, I will not look that up. You can do that yourself, or we can do it later on the blackboard where I'm not so distracted. But the result of that transformation is that your integral becomes in its most divergent piece proportional to just the inverse of a radial quantity. And with that, you recover again a log divergence with a certain lambda dependence, which turns out to be exactly the same as the one we had before, times A. And this is something which it's a technical step to find the divergence of that high dimensional integral. But the fact that you can do that by using this concept of hyperspherical coordinates, connecting such an iteration of Feynman diagrams is, I find, something quite neat. So I've never seen hyperspherical coordinates used in the context of diagrammatic field theoretical calculations, but here it becomes an extremely useful vehicle to find out that the divergence of the iteration of those diagrams is exactly functionally the same as the divergence for a single diagram. And the divergence is happening at rho equal to 0, and rho being the total momentum 0. So rho here in coordinate space characterizes the size of the system. And here, rho characterizes somehow the total energy encoded in all of the various momenta. So if you can get the energy not equal to 0 if you consider a single piece here going to 0. Also for those, you don't encounter a divergence. You only get this divergence if all of the momenta simultaneously go to 0. And that process you can collectively encode in this hyperradius going to 0, in the same way as you cannot tell whether the size of a certain configuration of particles is point-like if you only know that a certain subset of the relative distances is 0. And with that hyperradius, you have a single knob, which allows you, if I tune that to 0, the system is a point, or its energy is 0. And that is what we are doing here. And by doing that, we find that the iterated kernel is divergent. It's I don't know if this term is useful in that context, but it's infrared divergent. It's not a divergence which comes from the upper end of the integration region. And that is the, yes. Yes. So this integral here is something you can do that as well. It's not more difficult using the different coordinates. But if you write this out, which I'm too lazy to do now, you'll see that transcription immediately. That is the only thing you're missing. Okay, so now I found that this trace of n, k to the power of n, is equal, has the same functional divergence in E and A as the, for each power. So this f of lambda depends on the cutoff functions I'm using. So a Gaussian cutoff is a very useful choice. Another thing where this becomes lambda itself is when you choose a sharp cutoff regulator. So a theta function or a sharp momentum cutoff, then this boils down to a linear dependence in lambda here in the argument of the logarithm. Okay, so now what do we do with that? Now comes the dry mathematical part, which comes back to that point. So now I know that I have I have a very peculiar property of that series here. So taken as a power series in those numbers, eta nu, I know that in the limit of E going to 0, I have a divergence which is always logarithmically, regardless of what power I use here. And this is where my intuition ends and where you go to your favorite mathematician who knows something about infinite series and their peculiar properties. But he or she will tell you that in that case, where I have a log divergence, regardless of n, that there must be a corresponding accumulation point L where none of these eigenvalues eta nu passes over. And this point must also be above 1. And this is the crucial information. So I know that it diverges. And secondly, the divergence has the same logarithmic dependence regardless of to what power I take the elements of that sum. From that, the existence of such an accumulation point is guaranteed. So what does that mean in combination with the monotonicity of my eigenvalues as a function of E? Graphically. So I know that they are ordered. So if I take E going to 0, so I make it larger and larger, I find that an infinite number of those eigenvalues, not necessarily those ones, but I'll, for the sake of the argument, I do it, they go up and they all accumulate at this point, and they never pass above that. So, and this is brilliant because, or this is not yet brilliant. To realize now what that means is the brilliant part, because each of these eigenvalues here, which accumulates at L, passes through 1. And if it does so, it counts as a bound state. So the bound state energies are those where the various eigenvalues here, so this is minus bound state 1, this is minus bound state energy 2, and this is minus bound state energy 3. So, okay, this is also fine. I know now that I have a huge number not even that. I have
the scale lambda A. Where are you getting that when you're from the cutoff?
But it's an UV cutoff.
That's in the T.
That's in T, right? So it comes in. So this is, yeah, this is my favorite bubble sum, and in regularizing.
0 over rho, going from 0 to infinity. Rho is the sum over Ri square. Right? This is where the scale got. Because there was no other scale in the integral.
Can you say it again? I think so I did not write out all the factors which are in that integral. So there are those A's still floating around, and or the A's replaced by the coupling constants. So that was, I haven't written that. No, this was something I skipped. So I can, that was, so you have a product of those T matrices in the numerator. And with that comes in this product of low energy constants, which take care of the UV part of the integrations. That okay, so this is what I know from that.
What you evaluated? How do you know the balance for different balance of eta 1? Where you started out those graphs?
I don't know those. I don't know, and I don't care.
So it could have come from top to L also. Then you would not ever.
So could I have those eigenvalues? So the fact that this kernel is square integrable means that they are bounded from above. So there's an upper bound. I think you are right. I mean, there's nothing which tells me.
It starts from L and 1.
Yeah, so this could be the case. Why do I say that this? So why am I allowed to put all those etas below 1? So I don't have the argument, but what I suspect is that the properties of that kernel mean that, so if I take the monotonicity and reverse that, it means that going into the different direction, I would, if the thing does not become very small, so below 1, that, no. It's not so difficult, I think. So for each energy below 0, this sum must be convergent. So if it converges, it must not, and I would have the case where I have a lot of eigenvalues here above that, or the majority of it, such that there is no possibility that they cross 1, I would not have a convergent kernel anymore. So I think the argument, or at least this is to make that mathematically rigorous. A.
Between 0 and 1, it would cross 1 line. The question of it's below 1
or above. Now, I can, it's, so if it, you mean if it starts here? Yeah, again, I mean, I think the only problem, and I'm not an expert on the properties of such series, but the problem is always that for energies below 0, this sum is still convergent. And if you can still guarantee that with an infinite number of, so in principle, there's no problem with this starting here. Why should it? The only thing I'm interested in, or which is relevant for us, are those values which pass 1, which cross 1, and don't come back. So these ones are the bound state solutions. And the fact that I have such an accumulation point, meaning a point in where I have epsilon surroundings within which I always find an infinite number of those trajectories here, is enough to prove the point. It doesn't mean that there are other eigenvalues which stay below, come back and end up somewhere here. The only important thing is the ones which cross 1 once. And this is guaranteed through that monotonicity and the fact that I have an infinite number of them starting below below 1. And this is where the argument goes a bit back and forth. Okay, so the final step in that business now is that if I know that, what is the number of eigenstates? Or so now I have found, I have derived that in this limit e going to 0, for this particular kernel function corresponding to identical particles, I find that for an infinite scattering length, I have an infinite number of bound states. I don't know what that number is, but the ingenious thing now is, and what it must match, is the result of the alternative derivation of that by Yefimov himself. The two numbers should match. And this is something what actually comes out. So the number of bound states is proportional to the trace of K divided by that L. So the trace is the sum, and all the elements in that sum limit E going to 0, A to infinity, is then the number of states accumulating up there. And that number is proportional to the logarithm of A. And now I write it like the alternative derivation times the inverse of the range of the interaction, which is something which is parametrized with our lambda. So the momentum cutoff is inverse proportional to the range of the Fourier transform of that interaction. And this is the result which then matches or ties together this derivation and Efimov's derivation, which goes a completely different route. Okay, now let's connect that to, or look at that from an EFT perspective. So this sounds all very few body quantum mechanical without a lot of EFT content, aside from the usage of our EFT interaction for the two-body amplitude. So now this is a very different and unconventional way of looking at that problem. So assume that we would have done this calculation meaning we start from our leading order theory, which defines an interaction like that. So so from this simplest Lagrangian, which was the Pionless leading order Lagrangian, or is, I derive this amplitude. And if that is a legitimate starting point for a more accurate description of atomic or identical bosonic systems, it should give me a cutoff independent or renormalization scheme independent result for also the three-body amplitude. So, and okay, this is what, and the way I do my three-body calculations is exactly like that. So I do this analysis, and what I find out is that in the limit of A going to infinity, I don't get cutoff independent results. I get this result where I find that the number of bound states accumulating at 0 depends on that cutoff. So if I interpret this function here differently as something where in the course of the renormalization, I fix A, so A does no longer float. This is not the limit I'm taking. I fix that to be some value, but I change lambda. Now I have also a divergence, which is now the UV divergence or UV divergence. But in any case, I get a quantity which in my theory should be lambda independent, and the number of bound states close to threshold should be independent. So a theory is of no use if it predicts me an arbitrary number of bound states in the region in the low energy region where it should be predictive. And that renders it completely useless for that course. So what do I do in order to overcome that? And yeah, so the EFT prescription or framework now tells me what is the simplest way to modify that kernel. So that kernel, the connected kernel, is the source of the problem. So there I get a scheme dependence in. Now, the simplest way to modify that kernel here with a respective term adding to the Lagrangian is a three-body vertex. So with that, this kernel here, the Easter egg becomes augmented with a, so what is that in terms of Easter eggs and so on, with a, yeah, with a six-body vertex. So you're not up to jokes this morning, I think. So if I do that, the kernel structure is modified. So, and this is the simplest modification I can systematically introduce starting from the Lagrangian. I realized, okay, if I start with the simplest piece, a three-body amplitude creates a signature of a non-renormalized theory. What do? I introduce a counter term which takes care of that, which is then, yeah, which also introduces an additional parameter here. So it must be renormalized to some experimental datum. And the kernel function then is modified. And that modification affects all of those traces here, which then are, and I hope you believe me that this actually happens, if you adjust this D0 low energy constant accordingly, gets rid of all that, and you destroy this phenomenon of an accumulation of bound states at the two-body threshold. Yeah, so this was the story about two bodies and a very strange or unconventional argument why also at leading order such a three-body counter term is important. And this is, I think, I don't know how many words have been used on this, this problem of using a theory which is defined with a certain number of field operators in an amplitude which entails in the asymptotic state a larger number of particles or momenta. And this is one of the, yes.
The threshold when the effects go away. Isn't that a scheme dependent statement? But the way you would set D would differ from scheme to scheme.
So you mean the choice I make to which I match this D0? It is, so the outcome, so whatever I predict then for this bound state, for example, so let's say I I find this, this low energy constant by not considering a bound state, but by considering a scattering between three objects. That's what I can do. And then I predict the bound state spectrum. It has a certain structure and so on. Alternatively, I use a different observable, so a radius, and then I do the same thing again. So I will get different results. But the results are expected to be close enough such that they fit into the uncertainty I expect at the order of my expansion. Right. So this is what I expect. In neither case, I should get a scheme dependence in the sense that if I take the regularization parameter to some value, I get fluctuations which exceed that this size of the expected corrections. But this, they should not yield the same identical result. So I fiddle, or I do, I treat the corrections differently in those cases. Yeah. So just the background for that. This is the problem at the moment when we want to apply such theories to larger objects. This is where we are limited in our trust in those theories. For example, to use even this theory for the description of, I don't know what nuclei, the largest nuclei we talked about, but assuming that we have the computational resources, do we get renormalization scheme or group independent results for uranium-235? This is something which is an extreme case where we apply a theory which is renormalized to the A = 3 parameters, and we apply it to a system which has a lot more components. And we see that something strange can happen here. And so do I have enough time? Yeah, so maybe in the last 2 minutes, I show you some colorful pictures. So this is where research begins at the moment. So the need for leading order terms like that was found via an alternative route there by, also Daniel was involved in that, but it was found, I think, already more than 20 years ago. What has been shown a couple of years ago was that if you do a four-body calculation, so focus on that graph only here. So you have here on the x-axis lambda, the cutoff, the range, the inverse range of the interaction. On the y-axis, you have B4, which is the bound state energy of the shallowest tetramer in units of B3. And the various dots there are results of now a numerical calculation. So in that system, doing leading order calculations is already something which is too difficult to do analytically. So what was done is first a leading order calculation, the red dots, is where we see that this seems to converge. And that's the first problem which makes you not very satisfied that even if you go to very large cutoffs, the convergence is something you somehow have to believe in. This is, but red is deemed to be convergent. Now, the green and purple markers indicate next to leading order calculations. So you go one higher up in order, meaning that you add to this Lagrangian momentum dependent terms which distribute derivatives, momentum dependence, in a Galilei or symmetry compatible fashion amongst the field operators in all possible ways. So there are a bunch of other terms where you can have derivatives squared here acting on the outgoing and so on states. So this is the next to leading order. And in the recipe of contact EFTs, these terms are treated in perturbation theory. So they are no longer in the power counting to be iterated to all orders, but only taken as perturbations. If you do that and you go with those low energy constants renormalized to some higher momentum observable into the four-body system, you find this, or your numerical algorithm produces a divergence. So unacceptably strong sensitivity to the regularization parameter. The way out of that is to introduce or to promote yet again for the four-body system an operator which is now the cousin of the three-body vertex, namely a four-body vertex, which absorbs this cutoff dependence and then yields by construction the blue triangles. By construction, I mean that we renormalized F here to the tetramer binding energy, and therefore it's by construction constant. And you then need to apply that to a different observable to test whether what you've done makes sense. And what does that show? This is B5. So then you can go with this theory renormalized in the four-body sector into the five-body sector, make a prediction for the five-body binding energy. And what you'll find is with your renormalization, presumably renormalized theory, the blue triangles which seem to converge. So from that, I want to finish with something a couple of colleagues, including one of your peers in the audience, is working on, and a hypothesis where you generalize that, or where you think you understand how that promotion of operators goes systematically. So each of these is by naive dimensional analysis suppressed. So D shouldn't appear at leading order. F shouldn't appear at next to leading order. But what we find is that in the three-body sector, I have at leading order this promotion. In the four-body sector, I have at next to leading order a promotion of a four-body term. Now continue that in the five-body sector, you would have find the need for a five-body contact at next to leading order. In the six-body sector at n cubed LO, and so on and so on. And this would then furnish a systematic way of renormalizing such a contact EFT for the application for the ground state, at least for bosonic systems, up to an arbitrary order, precision, and size of the system itself. I did not talk so much about that in those lectures because all of that is mainly driven by numerics. So we don't have any means to even, or I shouldn't say that, but I'm not smart enough to come up with any analytical means of that character which we talked about now in terms of kernel functions and isolated things. What we do is we throw everything in on the computer and do this analysis, which I wanted to discourage you from by considering all the diagrams in our Green's function. Nevertheless, this is not less complicated, but it's the practical way to do at the moment. So one name I just wanted to advertise was with whom or who is mainly driving that, amongst other things, is Martin Schäfer in Prague. And he is doing all those calculations up to very large particle numbers. But this is a different lecture on the numerical tools which enable insight into that. But that doesn't keep us from speculating and conjecturing theories like that. Okay, so this is by far now, I exceeded my time. Thank you very much. It depends. So it depends on the energy of those states. So your theory is expected to break down for momenta beyond a certain breakdown scale. So if my bound state is so deep, such that it's dominant, so this is a qualitative argument, but if a bound state is deeper, so can we raise that? Thank you. If a bound state is deep, its structure is dominated by high momentum modes in the language of external states. And those are not something my interaction is designed to describe properly. So if those states are there or not are irrelevant. There might be certain things which you could tell from, yeah, but that is something I'm not very familiar with. So if a certain analytical function, so the amplitude, the bound states are corresponding to the poles of the T matrix or this K operator, and there are some conservation theorems which tell you that if I make a smooth modification of that, the number of poles must not change. So those are things which, and when I say that the number of bound states changes, it's usually something I take from the numerical side, where those conservation theorems do not apply, because yeah. So, yeah, I don't think there's a rigorous answer to that. If you want to have so if you do a calculation for nuclei, for example, what is the threshold structure in the four-body system? So you have D plus NP, then you have a DD threshold, then comes the triton threshold. So this is about 2.2 MeV. This here is about 4 MeV. Then you have for a long time nothing, and then you have the of course there is the helium-3 as well. Then you have the alpha particle, and that gap is about 20 MeV. So the EFT I'm invoking, if it produces 3 body bound states where I expect in the range of validity only one. So in nuclear, we never observed another, but this one 3 body bound state, or those 2, helium-3 and the triton. If I produce another one, let's say here, that is still something which I assume is within the range of validity of my theory, because I also want to use that theory for the alpha particle. But if it is at 60 MeV, yeah, I'm not sure. But this is, so in general, this is the problem with bound states. Scattering is easier to tackle because you can always identify this one characteristic low energy scale, namely the relative momentum between projectile and target. In a bound state, I have to associate with the bound state a certain typical momentum, or I don't have to, but that's what's usually done, that I say the bound state energy is roughly something which is proportional to some q squared over to some mass. And from that, I estimate a certain momentum. And if that momentum is below the breakdown scale, which is set by the lowest excitation, the pion mass, then I say, okay, it's within or outside of the region of validity. But this is an estimate. There is no rigorous argument for using that.
So when you come back here at 55, the tank run from a it's still around there. You have questions, go and hunt it down.